Hello students, in this video we will study some basic parameters that are related to optics. This video is intended to understand the limitation of photolithography process while approaching towards nanometer technologies. So, in order to understand the limitation of photolithography, one has to understand some basic parameters that are related to optics, namely light diffraction, resolution, and depth of focus. First, let us focus on diffraction. Based on a wave nature of the light, when a light passes through this aperture or a slit whose size is comparable to that of the wavelength of the light, then these light waves gets diffracted and in turn creates an interference pattern as shown in this figure. Now the question is how to make the light not to get spreaded while passing through this slit. So there are basically two ways by which one can control it. The first method is by making use of a shorter wavelength in comparison to the slit size. The next method is using a focus lens which can be used to collect the diffracted light and enhance the image. So out of these, using a first method has some limitations just because of the shorter wavelength, which can damage the substrate as it carries more energy in it. So let us look at the second method. So to collect all the details that are being diffracted through the slit, one has to have a larger diameter of a lens. But we know it becomes quite impractical, and while using a finite diameter lens, we will obviously lose some high frequency information. Now, as shown in this figure, there is a collimating lens whose job is to convert the spherical wavefront that is generated by this point source to a parallel wavefront. And as I said before, the job of this focusing lens is to collect the light that are diffracted and reproduce the image onto the image plane. A more clear mechanism that happens between the mask or the aperture to the image plane is shown in this figure. Now, as you could be able to see that when a light passes through this slit, it gets diffracted to all the angles, and we use this focusing lens to collect those diffracted lights. And if at all, if this diameter of the lens is so large, then what could happen is you would have produced an image pattern or the intensity pattern something like this. But ideally, it's practically impossible to have a very large diameter of a lens. So losing this high frequency information, we would have a smoother intensity pattern as shown in this particular picture. Now we will look into the parameters that are related to focusing lens. So basically there are three parameters that are related to it. The very first thing is the numerical aperture, the second the resolution of point images, and the third is the depth of focus. As shown, we will deviate from this discussion of these three parameters in between, and we will slightly talk about this Airy Disc, which is an important parameter to understand about the resolution of point images. So let us head back to numerical aperture. So numerical aperture is a parameter that defines the ability of a lens to collect the diffracted light. So the higher the value of the numerical aperture of a lens is, the more the sharper details that it can imprint onto the substrate during the lithography process. Also note that the square of the numerical aperture represents the ability of the lens to gather the light. So based on the image on the right, one can express this numerical aperture as something like the refractive index of the medium times the sine alpha, where alpha is the angle between the center of the lens to the one of its edge. Now, if this angle alpha is pretty small, then one could approximate the value of sine alpha to be equal to the radius of the lens divided by the focal length of your lens. So the value of numerical aperture, considering that the value of n is 1, one could approximate the numerical aperture to be the radius of the diameter times or divided by the focal length of the lens. So a lens with a larger numerical aperture can capture higher order of diffracted light and generates a sharper image. So before we move on to the second parameter, that is the resolution of point images, we need to slightly deviate a bit to understand about Airy effect. Airy Disc is nothing but the interference pattern that is created when light passes through a circular slit whose diameter is comparable to the wavelength of the light that passes. So one can actually explain the interference pattern that is formed here by making use of Huygens principle. But we will not deviate further in explaining about this interference pattern from the perspective of Huygens principle. But I would suggest you people to just Google about this Huygens principle. It really fascinates you when you try to understand it. Now let's revert back to the point number 2, that is the resolution of point images. Consider the image that is shown over here, where it's an image of an Airy disc that is formed from a monochromatic light that passes through a small circular slit. Now let us try to add another source which is actually separated by an angle theta as shown in this particular figure. And when you add a second source, so these two sources would actually create two Airy discs as shown on this particular image. So one can observe that the image on the left is when the angle between the two sources that I shown in the previous slide has an angle theta that is greater than theta minimum. You could able to visually see that there are two Airy discs that could be resolved as a two separate image point sources. And now when these two sources are brought close together by reducing the angle between them, then these Airy discs actually moves close to each other, and once they reach a particular angle theta that is equal to theta minimum, the image on the image plane becomes barely noted as a two separate sources as shown in both these pictures. And again, the figure on the right is an image that is created when the angle theta becomes smaller than the value of theta minimum, and the two point sources actually overlaps and becomes indistinguishable from each other. That is, it doesn't seem that the image formed here is from the two sources. It can be shown that for a circular aperture of diameter d, the first minimum of this intensity pattern occurs at a value of theta that is equal to 1.22 times the wavelength of the light source divided by the diameter of your circular slit. The accepted criteria for determining the diffraction limit to resolution based on this angle was basically proposed by Lord Rayleigh in the 19th century. So the Rayleigh criteria for diffraction limit to resolution states that the two images are just resolvable when the center, that is as shown here, when the center of the diffraction pattern of one is directly over the first minimum of the diffraction pattern of the other one. So in both the cases it happens to be that the center of this exactly lies on the first minimum of this particular intensity pattern, and similarly the center of this intensity pattern exactly overlaps on the first minimum of the intensity pattern of the other one. And we know from the intensity pattern of a single light source that the first minima occurs exactly at an angle that is equal to 1.22 times the value of the wavelength of the light divided by the diameter of the circular slit. So based on this first minima of the intensity pattern, one can define the value of theta minimum to be equal to 1.22 times that of the wavelength of the light divided by the diameter of the aperture. And note that the value of theta is basically read in units of radians. Now one could actually convert the angular resolution that we have defined in the previous slide into something known as spatial resolution R. And recall that we have defined that the value of sine alpha, which is an angle between the center of the lens to the edge of the lens, as something like the radius of the lens divided by the focal length. Now, based on the image on the right, you could be able to see that when there are two light sources that are denoted by letter A and B, these two light sources actually produces an image on this image plane as A prime and B prime, and they could be separated by a distance x. Now, in order to convert this angular resolution into a spatial resolution R, we can use this particular diagram to do that. So as you could note that this separation of x is again returned as something like 1.22 times that of lambda times the focal length divided by the diameter of your lens. And this is the formula that we have seen from the beginning. The only difference between this theta and this is nothing but we have multiplied focal length of our device. So that is the conversion between the angular resolution and the spatial resolution. So once I multiply theta with the focal length of the lens, then we end up having a spatial resolution x, which is nothing but the capital R. And again, we can rewrite this spatial resolution in terms of numerical aperture based on the formula that is shown here. So it's a very straightforward substitution, and one could end up having something like 0.61 times that of the wavelength of the light source multiplied by the refractive index of the medium divided by the numerical aperture. And one can redefine these constants, that is 0.61 times that of the refractive index of the medium, as a constant which is given by the letter K1. Okay, so the value of x is nothing but the spatial resolution R, and that is what is being reproduced over here. So based on this formulation, a lens which is having a larger numerical aperture will be able to resolve the finer details. That is what has been reflected across this particular formulae, and it is also capable of collecting more lights, or in other words, it is capable of collecting more of the diffracted modes, right? So now let us move on to our last parameter of the optics, which is nothing but the depth of focus. So before that, you can try to solve this spatial resolution based on the value of lambda that is given and the numerical aperture of the lens, and you can also assume that the value of n to be equal to 1, which is nothing but the refractive index of your air. Okay, so based on that you can compute what is the spatial resolution. Yeah, so now we'll just move on to our last parameter. So as you could see from this figure, where the image on the left shows how a camera with a high depth of focus could able to collect all the background images along with the image that is focused here, whereas the image on the right just captures the image that is focused and all the background images becomes blurred. So this means that the depth of focus for the lens that has captured this image is small, whereas the camera that captured this image has a larger depth of focus. Now the obvious question is, why should one has to worry about this in lithography? As you will learn in the next lecture that in general the substrate on which we create transistors and circuits undergo several etching processes, and due to which the top surface becomes uneven, and over this uneven surface one has to imprint the pattern onto the photoresist. So while doing, if the depth of focus of the lens is less, then the exposure on the shallow regions will not get properly polymerized, so thus reducing the resolution. So in general you need a higher depth of focus in order to have the proper exposure. So here is a diagram that relates the numerical aperture to the depth of focus. As you could be able to see that the image on the left has a larger diameter, which means that we have a larger numerical aperture, but in turn this has a low depth of focus value, whereas the image on the right has a smaller numerical aperture, which in turn has a higher depth of focus. So now let us try to derive this parameter in terms of numerical aperture as shown here. Now, based on this Rayleigh criteria that is shown here, one can relate the depth of focus parameter in terms of path difference. So what I really mean here is, you could able to see that there are two paths that approaches this image plane, and at the limit of focus there are two paths that approaches, one from the center of the lens, the other from the edge of the lens. Okay, so obviously these two paths will have a difference between them, and what this Rayleigh criteria conveys to us is that this path length difference should not be more than lambda by 4. So we will try to extract what is the depth of focus based on this Rayleigh criteria as shown. So this lambda by 4 at a bare minimum supposed to be equal to the path difference between these two paths. Okay, so one of the path is given by the factor del, the other path is given by del times that of cos theta. Okay, so here the theta is an angle between the center of the lens to the edge of the lens. Okay, so now again one can do some algebra and use some trigonometry to further simplify this expression such that one can rewrite that the value of lambda by 4 at least supposed to be equal to del times that of theta square by 2. Now it is this del that defines the depth of focus. Now again, the value of theta, if it is quite small, then one can approximate this to be equal to the numerical aperture of your lens. And again, as I said before, the depth of focus is nothing but it's a parameter that is related to del, and one can rewrite the value of del as something like lambda divided by 2 times that of the numerical aperture square. And in general, the value of this K2 ranges from 0.5 to 1. Okay, so with this we'll complete our lecture. See you next time. Thank you.